Hello, my name is Matthew Harrison. I'm a farming system scientist at the University of Tasmania. In this presentation, we'll be looking at the productivity and economic costs of transitioning farming systems to net zero emissions under future climates. This project was actually part of a larger project that looked at the need to balance competing priorities. So the project arose mainly due to three aspects. The first one was the pressing need for the agricultural sector to continually adapt to the changing climate. The second one was burgeoning societal pressure to mitigate greenhouse gas emissions, and people have probably heard of net zero emissions aspirations. The third one was to improve social licence to operate, and part of that was through improvement in environmental stewardship. So the project focused on systemic and developing transformational interventions that are really at the intersection or the nexus between livestock productivity, farming systems profitability, and greenhouse gas emissions, and specifically net farm greenhouse gas emissions. So I think people probably would be familiar with the changing climate. So for Australia, these are measured numbers, they're not modelled numbers. So if we look at Western Australia on the left there, rainfall for about the last 30 years has been below average and trending downwards, and we have a similar story in southeastern Australia. We've also seen an exponential rise in the number of extreme heat events. Here I've shown the percentage of Australian land surface area subject to decile 10 temperatures between 1910 and 2021. Decile 10 means 10 out of 10, and you can see from about the year 2000 onwards we've had an exponential increase in the number of extreme heat events. So this project, called the Nexus project, used real case study farms up the entire eastern seaboard of Australia and also in the west of Australia. The ones on the east looked at farms spanning more than 2,500 kilometres or more than 1,500 miles apart, and they were from a range of livestock farming systems, mainly beef and sheep systems. In this presentation, I'll focus on the part of the Nexus project that I led, which was the case studies in Tasmania, which were a beef production enterprise in the northwest and a sheep production enterprise in the middle of Tasmania, which is called the Midlands. As I mentioned before, there are case study farms in the west. These are at Merredin, I'm not sure how you pronounce it, Wajin, I probably pronounced that wrong, and Kojonup, and that's quite different rainfall across those three sites. So if you actually look at how those sites look, they're quite different, and we deliberately chose them in that way because they're in very different, they're not just different production systems, but they're in different agroecological regions. The northern Queensland site is a tropical site, so you really have two seasons and you have that rangeland-like environment that looks like this. The eastern Victoria site, more temperate, rolling green hills like this with very different pasture types. The site in northwestern Tasmania, which we'll focus on a bit more in the presentation, very cool maritime environment. And the site, one of the sites in the Western Australia one was somewhat semi-arid, so it's typical of almost mallee. It was called mallee area in the local area, so it's lower rainfall, hot dry summers, so somewhat Mediterranean. The project actually worked. We had an expert group of farmers, consultants and regional experts, and we call that, and I'll call that throughout the presentation, the Regional Reference Group, or abbreviation RRG. We had two case study farms in Tasmania, and the Regional Reference Group informed future industry challenge, and we actually modelled 4 thematic mitigation adaptation bundles, and they comprised a whole bunch of individual farming systems changes. We simulated future climates, 2030 and 2050 climates, underpinned by more extreme weather events, and we developed a specific methodology for that. We also had webinars by a group of scientists and industry practitioners in a range of areas, ranging from animal genetics to storing carbon in the landscape, and we used that information to develop transformative adaptations. We did a whole bunch of biophysical, economic, and other sorts of modelling, as well as social research. The main metrics that I'll talk about in this presentation are productivity, profitability. I won't talk about social licence to operate, although I do touch on social aspects. It was a very iterative project, so the outputs, once initially arrived at from the simulation models, we would take back to the regional reference group, for example, supplementary feed, and we would say, is this look appropriate for the amount of silage fed to your farm? And the regional reference group would probably say no, and we'd adjust the model inputs so that we'd more closely align the baseline modelling system with what the regional reference group expected. So that's stocking rate, supplementary feed, seasonal pasture production, and other variables. So in that way, we calibrate or ground truth our models, but the regional reference group can also gain confidence in the modelling processes that we use in that way. We also did what was called an involve and partner activity, where we piloted one of the initial greenhouse gas emissions mitigation options on another case study farm in northern Tasmania, and that was actually feeding biochar as a feed supplement to cattle. And I'll talk a bit more about that later in the presentation. That was an avenue for on-farm demonstration, for adoption and impact. One of the presentations was in Burnie, which is in northwestern Tasmania in 2020. Not a presentation, but a regional reference group meeting rather, where we solicited feedback on the modelling and refined our modelling based on what they said, and part of that was online. We had another meeting in the far northwest, which was at Stanley in May 2022. So one of the case study farms, if you can see the diagram on the lower left-hand side of the screen, was in the Midlands, which is essentially sort of in the centre of Tasmania and slightly to the right, near a place called Campbelltown. Annual rainfall at the moment is about 580 millimetres a year, which is relatively dry for Tasmania. So rainfall in Tasmania follows a rainfall shadow, so it's higher in the west, and as you go towards the east it drops off, and as you go from north to south it drops off. So Hobart, where that red dot is, has amongst the lowest rainfall in the state and the second lowest in Australia. We also did pasture trials on this Campbelltown farm, and that was a good avenue for demonstration as well, to show what the latest genotypes are and how they perform in the area. And we did model some of those. We actually modelled tallish clover, which you can see there in the bottom of the screen, in our models. So we used some of the most recent experimental data in the model. The other farm was at Stanley in the northwest. It had much higher rainfall, about 940 millimetres per year. It was at a place called the Nut, which is an old volcano, and you can see it sticking out of the ground there. But higher rainfall and very different soil. So it's a red ferrosol, sort of high iron content, high clay content, and generally higher fertility. What we found overall was beneficial impacts of a changing climate for Tasmania. So temperatures increased by 6% by 2030 and about 11% by 2050, mostly late autumn, early spring. Rainfall declined, although it was very variable and difficult to get a signal, mainly during winter, which is actually a win, but also it reduced during spring. So that contracted over a 30-year simulation the duration of the growing season. Some growing seasons increased, but most of them decreased. Pasture production actually benefited from warmer winters because we got slightly more mild winters. Growth is somewhat constrained at the moment from winter time, not due to moisture, and so therefore you alleviate that temperature constraint a little bit and growth increases. It flattened the high spring growth rate, so we didn't quite get the peaks that we used to. Lamb mortality, because of the colder winters, dropped off a bit in the model, and we had slightly warmer springs, so that benefited it as well. So overall, future climate impacts on Tasmanian livestock enterprises are relatively modest, even beneficial, but we still do need greater agility in management for resilience to extreme events. Part of the modelling that we showed was that by 2050, soil carbon sequestration went down by between 45 and 133%, even in the absence of positive changes in pasture growth. And that was due to warmer temperatures, warmer soil temperatures, greater soil respiration, and lower pasture growth on one of the farms. So soil carbon, even if pasture growth goes up, if temperatures are going up and if rainfall remains unchanged, soil carbon can go down. So then we developed, with the regional reference group again and with input from others, what we call these adaptation-mitigation bundles. So we developed 4 themes that we modelled, which is scenarios, which we imposed on the baseline of each of these farms. One of them was called low-hanging fruit, which is simple, immediate, reversible changes suggested by the regional reference group. Another one was towards carbon neutral, which is to reduce year-on-year greenhouse gas emissions through a combination of interventions like carbon sequestration and emissions mitigation. Another one was income and climatic diversification. So therefore, if you get more droughts in future, and remembering that the Nexus project was conducted across the whole of Australia, so not necessarily just Tasmania, these interventions were applied consistently across the country. Can you diversify your income streams so that you're not entirely reliant on grass production from rainfall? Part of that was through climatic exposure. So part of the modelling we did was buying another farm enterprise in a distinctively different climatic zone. And so if you get a drought in one region, you might not necessarily get a drought in another region. And that's what large corporates do, at least in Australia. The final one that we looked at was transformational adaptation mitigation bundles. Part of that was, again, it come from a question from the regional reference group. They were interested in this towards carbon neutral one, but part of the question was, well, we don't just want to reduce emissions, we want to be net zero. So what is the cost of being carbon neutral? So for this, we stacked together or combined multiple carbon sequestration or emissions mitigation or carbon dioxide removal options together, such that the net farm emissions were negated to zero on a year-by-year basis, and we compared each option with the cost of purchasing offsets, which in Australia they're called ACCUs, or Australian Carbon Credit Units. So one ACCU is equal to 1 tonne of CO2 equivalents. So going into a little bit more detail, the historical run was done with real climate data between 1986 and 2005. The baseline farms were centred on climate horizons of 2030 and 2050. The low-hanging fruit had things like increased root depth, improved soil fertility, improved animal genetic feed conversion efficiency, shifting forward calving time, and a small increase in stocking rate. The towards carbon neutral had a methane vaccine, which was done to 30% of livestock on farm, that number being informed by the regional reference group. Planting trees, the northwestern farmer was more interested in buying additional land for planting trees, so we said we'll buy 50 hectares for planting trees, and that would be insetting carbon emissions. Another part of that was renovating all available pastures, which are mainly grass, sort of perennial ryegrass pastures with lucerne. The income diversification one was to lease part of the land with a wind turbine company, and another part of it was buying and managing an additional farm in a different part of Tasmania. So this farm was in the northwest, and we looked at purchasing a farm in the northeast with 750 hectares. And part of the transformational one was feeding Asparagopsis, or red algae, livestock feed supplement. We assumed that that would be fed to 80% of weaned livestock. We assumed that no unweaned livestock would be fed it. Given the uncertainty in the literature at the moment, we assumed no livestock change, so no productivity co-benefit, although it could have a co-benefit. We looked at feeding biochar as a feed supplement to all weaned livestock, which is exactly what we're doing on the unfarm experiment. And the other part was a transformational change in genetic feed conversion efficiency, which, talking to scientists and expert practitioners in the area, we assumed a 20% gain by 2030 and a 30% gain by 2050. Now, what did we find? Well, this chart actually shows the trade-off between mitigation and cost at 2050. Now, I'll take a little bit of time to walk through this because it's a complicated plot. On the X, we've got annual net greenhouse gas emissions reduction, and on the Y, we've got net greenhouse gas emissions reduction. We've got the cost of net greenhouse gas emissions on the Y-axis. Anything below the ordinate axis, so below the zero line, is a profit. Anything above the zero line comes with a cost. Now, the X there is not actually an X-axis, so in the traditional way where you increase to the right, it's just a scale. So that scale that I've shown there is 1,000 tonnes of CO2 equivalent. So the wider the bar, the more mitigation that option has, and this is called a marginal abatement cost curve. So Asparagopsis had the greatest mitigation of all options examined. So it had about 1,800 tonnes of CO2 equivalents mitigated. Planting trees and the transformational feed conversion efficiency had the second most. If we look at feed conversion efficiency per se, feeding biochar as a livestock supplement and renovating pastures with lucerne, they actually had the biggest benefit and economic benefit, whereas increasing soil fertility, planting 50 hectares of trees, Asparagopsis and using a methane vaccine came with the biggest cost. We also looked at adoption, which is a social factor. These were rated again by the regional reference group, all of them except for planting trees and for the transformational feed conversion efficiency were rated as relatively adoptable. These two weren't. Transformational feed conversion efficiency was because it's not available, and planting trees because you actually need quite a lot of knowledge to plant, establish, use the right fertility, time of year to actually get trees going. What about productivity? And so again, we saw trade-offs between productivity, profit, and greenhouse gas emissions mitigation. So on the x-axis, we actually have total tonnes of CO2 equivalents there. We have tonnes of livestock produced, so tonnes of livestock sold in any given year. On the y-axis, we have farm gross margins, so going from 500,000 to 750,000 Australian dollars. If we look at the size of the bubble represents relative change to the baseline. So the bigger the bubble, the bigger the change to the baseline. Now, if there's a plus in the brackets, that means that the emissions relative to the baseline, which are that star there, have gone up. If it's a negative in the brackets, that means that the emissions relative to the baseline have gone down. Now, again, the same as before, I've got the ease of adoption in terms of the colours. So the extra farm by the regional reference group was rated as low adoption because it's a long way away, you'd need extra machinery, you'd need extra labour to manage it, so it was classed as low adoption, even though it was one of the most productive and it had a relatively high effect on profitability relative to the baseline farm. So again, this demonstrates trade-offs between productivity, profitability and emissions. Don't just focus on emissions, remember the other key factors, and it's not only productivity and profitability, but things like social licence and adoptability as well. So increasing stocking rate, buying an extra farm, changing calving date or moving it slightly forward, increased emissions. And that's due to the tight coupling between emissions and productivity. Leasing part of the farm to wind turbines didn't do anything to emissions, and the reason for that was because the wind turbine company we assumed owned all emissions. If the farm owned the emissions, that would be very different. So that actually improved profit but did nothing to emissions. And we had multiple options that actually reduced emissions, transformational feed conversion efficiency, reducing them to the biggest extent, followed by lucerne, followed by more modest feed conversion efficiency improvements. So really anything above that star there improved profit, anything below it reduced profit. Asparagopsis, as I showed before, or feeding Asparagopsis or red seaweed as a livestock feed supplement had the biggest effect on mitigation. So too did buying an extra farm in a positive way, so it increased emissions. So overall, transformational feed conversion efficiency and purchasing an extra farm had the greatest influence on productivity and profit, whereas Asparagopsis, planting trees and methane vaccine had the greatest mitigation effect. What about the shifts between interventions with climate change? Not much. So you can see that relative to the difference between, for example, altering lambing date and stocking rate relative to Asparagopsis is much the same in 2030 as it is in 2050. So the impacts of climate relative to the impacts of farm system intervention were pretty low. Getting to the crux of the presentation now, what does it cost to transition to net zero emissions? There's a fair bit of information in this slide as well, so I'll take a little bit of time to walk through it. The net emissions of the farm were about 4,000 tonnes of CO2 equivalents per year. If you wanted to do nothing and purchase all of those emissions offset to zero, which you could do theoretically, you would cut more than half of your farm gross margin, half of your farm income. So gross margin is calculated as total revenue less expenses. So you lost about 319,000, assuming that your gross margin was 550,000 per year. So it's a big cost, which in a way is quite a good thing. It's serendipitous because if it was the cheapest way, then everyone would do nothing and offset their emissions, whereas the atmosphere wouldn't actually see any net removal of CO2 and therefore any net mitigation of global warming. Buying Asparagopsis reduced emissions by 1,800 tonnes down to 2.1, and the cost was actually less than purchasing credits outright, so it cost about 172,000 at the cost that we used. Stacking together Asparagopsis as a feed supplement plus planting trees reduced emissions further by another 800 tonnes of CO2 equivalent, and it was slightly more profitable because we assumed that trees would have a slight co-benefit for productivity. So that reduced, so your gross margin's now gone from 550 to 478, so the cost, which is that blue segment, is less. We then had our first carbon neutral package, so we've reduced the total emissions down to 1,000 tonnes of CO2 equivalents. Total profitability is actually increased, so we've got Asparagopsis plus planting trees plus transformational feed conversion efficiency for your livestock. Your productivity is increased and your profitability is increased. We still have to offset about $78,000 worth of credits to get ourselves to net zero. And the final one, CN2, that we looked at was planting more trees. So Asparagopsis feed supplement plus planting trees, 85 hectares, which is not minimal, plus transformational feed conversion efficiency. So your baseline profit has gone from 550. It doesn't really matter what it was, it's just the relative change. 550 up to 638. So you've actually gained in income. So you've stacked together Asparagopsis plus planting trees plus transformational feed conversion efficiency, and you've gained. So what does it cost to be net zero? Well, it ranges from very costly, more than half of your income, to a net gain. There's another way to do it though. So you could have the three same steps, Asparagopsis plus planting trees. You might renovate pastures with lucerne instead of opting for transformational feed conversion efficiency. And again, you get a slightly different result. So you can reduce total emissions to about 1,000 tonnes of CO2 equivalents with planting lucerne, and it can be reduced to zero by, again, planting some more trees. So you've got 50 hectares of trees for CN3, and this 85 hectares of planting trees for CN4. So you've gone from 550 to 571,000. So not quite as profitable as the carbon neutral 2 package, but still profitable nonetheless. So to answer the question, what does it cost to transition to net zero? It costs nothing if it is provided that you stack together synergistic interventions that look at enteric methane mitigation, carbon sequestration, and potentially buying credits, but particularly productivity co-benefits. So if you want to narrow that down into, say, something more simplistic, one unidimensional sustainability indicator, which is what we've done here, how do they actually compare? Now, I've talked about what these abbreviations are here, but I won't talk about them there. I'll talk about the main results. You can see the components of each scenario within each of these bars. So greenhouse gas emissions, profitability, and productivity. The three carbon neutral packages, those interventions that resulted in a net zero farming system, were the most beneficial in terms of one sustainability indicator, and that's because they have a combination of enteric methane, carbon sequestration, and productivity co-benefits. The income diversification was one of the least beneficial in terms of sustainability because it didn't have any impact, or it had a negative impact on greenhouse gas emissions. The baseline had the lowest sustainability, so that indicates the cost in terms of sustainability of doing nothing was greatest. Now finally, I'll turn my attention to the involvement partner or on-farm activity, where we fed biochar to livestock on farm and did a number of workshops on surrounding farms in Tasmania. We fed the calves, younger calves, on a farm near Deloraine, which is in northwestern Tasmania. It was a commercial biochar. And the reason for that is because biochar is said to reduce enteric methane. We didn't measure enteric methane in this experiment though. It's said to improve animal growth rates, which we did measure live weight gain. It's also said to improve soil organic carbon, so if they eat it, it's indigestible, goes through in the manure, and then dung beetles can carry it through the soil into the soil, and you can there's a farmer in Western Australia who's done it for a long time, and he says that you can see the black tunnels from the manure into the soil. So it's could have soil carbon benefits, could have growth rate benefits, could have enteric methane, could have win-win-win. So we're measuring biochar consumption, live weight gain, and manure organic carbon. We're also looking at impetus to change, so the social side of things through on-farm discussions on the case study farm near Deloraine, but also other farmers who have done it for a long time. So we essentially speed up. We look further down the track, farmers who have fed biochar for 10 years. And we're modelling the impact of those three sub-dot points there, methane, growth rates and soil carbon on on-farm emissions. And we've done a number of workshops. They've been on the case study farm, they've been in the far northwest, they've been in the northeast, and through those we're measuring propensity to change, but also gaining feedback as to why or why not people would be interested in feeding biochar, but also other feed supplements in general. The product that we fed is an ex-forestry product, pyrolysed, heated to a very high temperature in the absence of oxygen. It looks a little bit like charcoal there. It's fed as a loose supplement. We add salt at the beginning and then slowly wean them off the salt. Can also be fed as lick blocks. We towed the troughs behind the motorbike from paddock to paddock. We found that they didn't necessarily like it when it was wet, and so therefore we bought a covered feeder later on to keep it sheltered out of the rain, and we found that they tend to consume that more. I'm not sure whether this video will work, but it seems to be as they like it, and just walk away. We found that their consumption varied throughout the season. We found that anecdotally that their winter coat of the biochar fed mob was lost earlier than the winter coat of the control, so we did controls and treatment mobs, and so I think overall the farmer was quite pleased with it. We also looked at pasture composition because this was on a commercial farm, so we looked at pasture composition to ensure that the control and the biochar treatments weren't consuming radically different pasture masses, and they weren't. We looked at botanical composition. There was no real difference between the two. It was mainly grass followed by legumes. We measured live weight gain, and these numbers have a lot of animals in them. I think we had 180 at the start, and then we had about 70 at the end because the farmer sold some of them. But if you look at the open dots, the control, and the closed dots, they're within the standard error of the variation between them, so we didn't find any significance between the live weight gain of them. But other experimental research has shown that there is. So biochar produced from rice husk showed about a 24% difference in live weight gain from cattle fed 1% biochar over 56 days. So if you compare that orange bar to the blue bar. And the reason for that may have been because the biochar fed cohort ate slightly more, their intake was slightly higher, although the differences are not significant. So the outcome of that in the experiment, we think, is that biochar ain't biochar. So there's very different types of biochar, and that has implications for potentially energetic value, intake, and also live weight gain. So future work could compare impacts of live weight gain, soil carbon, greenhouse gas emissions of different types of biochar. Now, a lot of this has been published. So carbon cash cattle in the climate crisis, that's freely available online, as well as costs of transitioning to net zero emissions under future climates. That's under review in a peer-reviewed journal, but the full paper is also online if anyone wants more details. So just to conclude, we found modest, even beneficial impacts of climate change out to 2050 in Tasmania. We found that even though pasture growth could potentially increase, soil carbon sequestration will go down, so that's the rate of gain of soil carbon, and for the northwestern farm, soil carbon stocks could actually fall. We found significant trade-offs between productivity, profitability and mitigation. So transformational feed conversion efficiency and purchasing an extra farm in a different climate zone had the greatest influence on productivity and profit, but they often also had the biggest impact on emissions. Asparagopsis had the biggest mitigation effect on emissions, so reduction in emissions, followed by planting trees and using a methane vaccine, noting that methane vaccines aren't commercially available yet, at least that I know of. The influence of farming system intervention had a greater effect than the effect of climate change. The cost of purchasing carbon credits to offset all farm emissions was greater, so it's a disincentive to offset and an incentive to inset, which is serendipitous really, because if purchasing carbon offsets was the cheapest option and you didn't have to do anything, you would probably expect that human behaviour would be to follow the most easiest option, even though the atmosphere wouldn't see any net benefit. Multiple pathways were found to net zero. The pathways that include interventions for enabling a co-benefit generally come with the lowest cost. So if you stack together interventions that have enteric methane benefit, have carbon sequestration and have productivity co-benefit, those were most conducive to the lowest cost and even slightly profitable pathways to net zero. I didn't really show it in this presentation, but planting trees had much greater effect on farm emissions than did soil carbon sequestration. As I said before, interventions that reduce enteric methane, sequester carbon and elicit productivity co-benefit tend to be more profitable. And even though you can have something that seems prospective in terms of profit, productivity and emissions, there's still many other factors that influence adoption. So things like knowledge, skills, can form barriers to adoption. So we showed that, for example, those carbon neutral packages were highly prospective and even profitable, but people were not inclined to adopt them due to many other factors. So complexity and adoption. So wider disciplinary studies should look at social and indeed psychological factors influencing adoption. So that's really all I wanted to say for today. Thanks very much for making it this far.